All right, gonna go over a couple things for class. We're mainly gonna be talking about the lungs today, so that's kind of what we've been hitting on over the last couple days. But first thing I'm gonna start with are the lungs. I'm gonna kind of go over an overview of the lungs, kind of some of the layers and the structures of the lung, how we build negative pressure and things like that. We're gonna go over that, and then I'll go over gas exchange. So PAo2, how do we get oxygen to the mitochondria, or to the electron transport chain on the membrane of the mitochondria for that exchange of CO2 that's coming from the citric acid cycle, and then how do we get it to the lungs? And so I'm going to go over gas exchange as well. Then we're going to go using hemoglobin. Then I'm going to go over gas transport. With gas transport, I guess gas exchange would be more the pressures that fluctuate with CO2 and O2 kind of coming in and out of the alveolus, but the gas transport, that I'll be using the hemoglobin, I'll go over that. And then I'll talk about alveolar ventilation, I'll talk about TV values, TPV, and then we'll talk about AV and kind of how all those things correlate with ventilation. So I'll get started with this first part, and that'll just be an overview of the lungs, okay? First thing is we need to kind of blow this up a little bit. So this part right here, this is going to be called our trachea. Okay, and then this will be called our alveolus. Alveoli, if we were talking about just one of them. So yeah, that's our alveolus, okay? So I'll title this one lungs. Something that's really important about this is I kind of want to describe a couple layers here. So this is called this right here is a layer around the alveoli. And this is called the visceral pleura. Now the second one here is another membrane around this, and we call this the parietal pleura. So we have the alveoli, or the alveolus, we have the trachea, we have the visceral pleura, and the parietal pleura that exists within this lung structure. Another thing that we have is we have this layer within the inside, and we call this the water surfactant layer. And we'll go over layers and things like that later in another video, but this is kind of where I want to start with this. So we have those things that we want to establish. One other thing that I want to draw on here are the ribs. I want to show kind of where the ribs are at. Okay, so we have the ribs coming on the outside here. What ends up happening is we also have another structure right here that's pretty important. It's called the diaphragm. Okay, that's called the diaphragm. One thing that we need to know is when we do inhalation, and we'll talk about this actually in a second. I probably want to start with another concept called respiratory systems. First, okay? The first thing is this concept that as I guess as air comes in, so pressure will go from high pressure to low pressure. So we want to keep that in mind when we talk about how do we get air in, how do we get air out of the lungs. The second thing that we want to know is something called Boyle's Law. And I'll talk about this again in the next section, but Boyle's Law basically says that if you increase the volume, the lung expands, then the pressure decreases. If you decrease the volume, then your pressure will increase. It has to do with surface area and physics, but if we understand those concepts, we'll understand how airflow works. The last thing that I want to mention on this is that we have those three layers that I had mentioned. We have the alveolus, we have the visceral pleura, and then the parietal pleura. And what ends up happening, let me make sure I put those in the right order, yeah. What ends up happening is this. You have the ribs that pull on the parietal, which in turn pull on the visceral, which in turn pull on the alveoli. Which then pull on the alveolus, right? So when they pull on the alveolus, then we get that expansion during inhalation, okay? So now I want to touch on inhalation and exhalation. So inspiration and expiration. Okay, when we talk about inhalation, there's a couple concepts that we want to discuss. The first being that inhalation will increase the ribs go up, okay? When we breathe in, your ribs come up and out. Then your diaphragm goes down. When we do this, the radius, our area increases and our pressure will decrease, okay? So what did we say up here? We said the air is going to go from high to low. So if we lower the pressure within the alveoli because we increase the radius, then we're going to actually see something really cool happen, which is that you can get a negative pressure within the lungs and allow air to come in. Now we know that partial pressure, that the pressure of PAo2 sits at about 160 millimeters of mercury. And PAo2 sits at about 23. That's going to be important for later, so we'll keep that in mind, okay? All right. Now, I want to hit on inhalation a little bit more. Yeah, so when I say increase R, I guess we're not ready for that concept yet, but it's increase volume. We're going to increase volume, decrease pressure, and in turn, this increases the parietal space. This right here in between, this is called the parietal space. Okay? Parietal pleural space. So we increase the parietal pleural space, okay? PPS. And in turn, like I said, the pleural space becomes more negative, right? Perfect. Exhalation. This is breathing out. Okay? When we breathe out, I believe we use our ribs a little bit, but when we breathe out, we're decreasing the volume. It's going to increase the pressure. If the pressure increases, then we know that the PPS, parietal pleural space, also is going to decrease. Okay? If the pressure increases greater than the pressure of ATM in the atmosphere, then we have what we want, which is for release of gas through exhalation. Okay? Hopefully that makes sense. Okay, and then it keeps collapsing until you have this parietal restraint, pleural restraint, which is the ability to not collapse too deep. This leads into my next topic, which is going to be pneumothorax. So with the pneumothorax, we have something that causes a hole within the lung. Within the lining of the lung. This could be especially dangerous because you get fluid in there or whatnot, but in this case, we have this hole. With the hole, it actually causes the air inside to decrease. Negative pressure. So we have a collapse. And then we don't resist it. And we end up having that collapsed lung. So the treatment is to put a tube within there to suck out fluid, which allows the treatment of this is it's put a tube in, suck out the fluid, which will then allow the lung to expand. And with that expansion of the lung, then we allow for volume to increase, which has an inverse effect on pressure, and pressure will decrease, and we allow for that expansion. But this has to do, pneumothorax has to do with this parietal pleural space, which has a negative, I think, 3. Yeah, negative 3. This is what keeps the lung inflated. So when you open that up, you get air in there and pressure becomes really high. Not good, because then we have that collapsed lung. Okay, I think I touched on everything I wanted on this part. Lapierre's law. So, next thing I want to talk about is this thing called Lapierre's law. Laplace's law. And that is pressure equals 2T over R. R stands for radius, and T stands for tension. R has greater significance. Okay? R has a greater significance. So, one thing that we can think of with this is, with R, we can think of smoking. Okay? Smoking. And what ends up happening with smoking? Smoking has an effect up here. Smoking can do two things. One, it increases alveoli to combine. So if you had 3 separate alveoli like this, they would turn into 3 continuous alveoli. What does that do? That increases R, which decreases pressure, right? So we know that inhalation is easy. Check mark, it's cool, it's good, it's easy, right? Inhalation. But this also does one other thing, and it inhibits type 2 cells, which happen to involve surfactant. And if you decrease those, what you end up causing is they're going to decrease tension, specifically surface tension with water. And if you decrease the surface tension with water, then what you end up causing is a decrease in resistance. So the smoke destroys resistant cells that resist. So basically when you breathe in, it's easy because compliance increases. And you stretch, and there's less resistance because there's not these type 2 cells that create surfactant. Am I saying that right? Okay. Yeah, so all I have is that it's caused by COPD, and that stands for chronic obstructive pulmonary disease. And they just have a hard time exhaling because they don't have the resistance to do the collapsing of the lung, pulling it back in. Okay, so that's what smoking can do to the lung. When we talk about tension though, tension might be a little bit easier to explain here. Tension, we'll bring it up here. These water molecules, H2O, they interact via hydrogen bonding. And when they interact through these hydrogen bonds, what ends up happening is they create something called surface tension. Now type 2 cells secrete something called surfactant, which gets involved and breaks these bonds, so it actually decreases tension, which decreases pressure. But we also know that tension, when it's increased, it increases pressure based off of our equation here. Okay? Let me make sure I got everything. Yeah, I got everything elastin. Yeah, so this, they basically destroy elastin. Okay? Okay, last thing. If we were to draw a graph of this, we would want to know about how respiration and inspiration, well, inspiration works if you got to breathe in harder or breathe out harder, right? So we would have volume over here, and on this side we would have our pressure, right? And if we were to just label these like this, normal would be kind of like that. Okay? If we had a restrictive condition, we call it restrictive lung disease. Then what this means is that it's hard for inhalation. Right? Because in this condition, in a restrictive lung disease, your R goes down. And your T goes up, which means your pressure goes up, right? And your elastance goes up. So if you use a solution on the lungs or cystic fibrosis, and cystic fibrosis inhibits type 2 cells, which we talked about up here, that the type 2 cells actually secrete the surfactant. Right? Now, if we did one more thing here, if we focused on inhalation, and we said, oh, we are dealing with an obstructive lung disease. An example of this would be smoking, which leads to COPD. We increase compliance. We decrease tension, decrease pressure, increase R. Smoking destroys, as we talked about, elastin, as mentioned here. So you can breathe in easy, but breathing out is really hard because the elastin's gone. So if you fill up the lung with saline water, you're going to decrease the tension, and you'll increase the compliance. So that's what we want to keep in mind when we're talking about these graphs, like that, okay? Okay. Moving on. Okay, so the next thing I wanted to talk about was gas exchange. I'm gonna slide this puppy down here just a little bit. Okay, so next thing I want to talk about is going to be gas exchange. So, what do we mean by that? Well, one thing that's really important, let me write this down. Okay, gas exchange, right? So what I'm going to do is I'm going to zoom in on alveoli right here, kind of like this. Okay, alveolus, alveoli, trachea, right? One thing we want to know are the partial pressures and how to calculate those. The other thing we want to know is some values in here. We call it PA, capital A, O2. And what does that value equal? It's 102 millimeters of mercury. We also want to know what is the CO2. 45 millimeters of mercury, right? Within the alveolus. Now, I'm going to draw a blood vessel coming through in this capillary exchange, right? So, we have a capillary exchange taking place. This is a blood vessel. Okay? That's a blood vessel. Okay, a couple things I want to draw here. The P little a CO2 value in here is 40, and the P little a O2 value in here is going to be equal to 102. So what we get from this is P big A O2 is equal to P little a O2, okay? So we know that oxygen wants to come in and CO2 wants to come out. Now, partial pressures, we have nitrogen, oxygen, CO2, and water. The partial pressure of nitrogen is going to be 74.9. Partial pressure of oxygen is going to be 13.7. The partial pressure of CO2 is going to be 5.2, and the partial pressure of water will be 6.2. We times each of these by 760, which is our atmospheric pressure. And this gives us a value of what the partial pressures are. Now what we really care about is this table that I'm going to draw right here. What I'm really concerned about in this case is, what's the percentage of these molecules in the atmosphere? And I kind of want to know what the oxygen is, so I know how much oxygen I'm getting in with each breath, right? So, what I tend to do, or what we tend to do, is we want to label these with their pressures. So, nitrogen, oxygen, CO2, and H2O. We know that in the atmosphere, 70% of the atmosphere is nitrogen. 21% is oxygen. 0.04% is CO2, and 0.046% is going to be our water. So one thing I want to mention is this. If we had a beaker here and this was filled with water, and within the beaker we filled this beaker with we filled it with fluid and then gas, and we put a cap on top, right? What we know, we have gas up here, right? Gases. What we know is pressure. If pressure increases, then the molecules go to the liquid phase and they join the water there. If the pressure decreases, then the molecules go into the gas phase. Okay? You go into this gas phase. So there's some solubility changing, but we know that pressure has a direct correlation and effect on penetration and movement of molecules within a solution or within the air. Now that we understand those things, I want to talk about a couple laws that we're going to want to know. The first law that we want to know is called Dalton's law. The second law that we'll know is called Henry's law. And the third law is called Boyle's law. And I've already mentioned that right up here. 3 laws, okay? Let's start with Boyle's law because it's the easiest. I've already told us that if volume increases, we know pressure decreases. They're inversely proportional. So then if volume decreases, then pressure will increase, okay? That has to do with Lavoisier's law, with pressure equals 2T over R. And we know that R has a greater effect on the actual function of that pressure. The amount of the pressure, right? Henry's law states that is about permeability. And so we know that CO2 is permeable, okay, and requires, okay, listen, it requires less pressure to dissolve or to, permeate the membrane. All right? Less pressure, permeate the membrane. Dalton's law, on the other hand, is going to be pretty important for us in terms of what we want to know. The reason we're doing all this is because we want to know what is it about Dalton's law that helps us understand the amount of O2 in the air. So PAo2, we're talking about the partial pressure of oxygen within the alveoli, is equal to FiO2 times PAtm minus PH2O minus this value that's given here. Oh, and this is at sea level. Okay, this value. Okay, PaO2 equals FiO2 PAtm minus PH2O minus P(a)CO2 over R. This is a different R. This is a gas law constant, R 0.85. Okay? And then we can use this equation to solve things. Now, a few things I want to point out. This is equal to 0.21. This is equal to 760 ATM. This is equal to 50 ATM. This is equal to 40 ATM, or millimeters of mercury. This here equals 0.85. I believe. Let me double check that one. Something that we want to know, okay, really quick, is that if you increase your PaCO2, that decreases your PaO2. Okay, one other thing, if you increase in elevation, PaO2 decreases. If you decrease in elevation, PaO2 increases, right? All right, I'm just checking to make sure I got everything. Pretty sure I did, so. Yeah, I got Boyle's Law, Henry's Law, and I got Dalton's Law all covered there. Good. Okay, that's how gas exchange works. Now let's move on. Let's keep it going. Okay, the third thing I want to talk about is gas transport. Okay, gas transport. Well, why is this important? Well, because the reason we're talking about everything else is to lead up to this, is to allow gas exchange to occur. We got to get rid of CO2, and we got to get O2, oxygen, into the body. And you know, in biochemistry, we talk more about why we need O2 and at the electron transport chain. But for this purpose, we don't really care about going into the details about that. But we know that it sustains life. Okay. First thing I want to talk about are the layers. Layers, okay? You know, I feel like I'm missing something right now. Huh. Guess I don't have any more with that. Okay. So this is something I want to talk about. I actually really like this section here. I'm going to just keep that up for a reference. But let's talk about layers. Let's draw another alveoli. Okay, let's go ahead and label this. So alveolus for singular, and then this is our trachea. Later we'll talk about this. It's called dead space. Okay, we'll go ahead and label that. Okay. One thing I want to talk about are the layers here. Okay. So the first layer around this, when we talk about this penetrating permeability of these gases, they go through all of these layers here. So layer number 1, there's 6 layers. Layer number 1 is going to be called the water / surfactant layer. Okay? Layer number 2 the second layer is important because this is called the alveolar epithelial layer. Now there's 2 things that are important with this. You have type 1 cells and you have type 2 cells. Okay? Type 2 cells have something interesting about them. They produce surfactant. Which in turn decrease tension, surface tension, decrease pressure, which increase volume. So they allow for this inhalation, this expansion of the lung, of these parietal, visceral, the pleural layer, these layers of the pleural, these lung layers, that they can expand and we can get air into these alveoli. So we have all these pressures that deal with type 2 cells. One thing that we want to mention here is, well, I think I actually mentioned everything I need to for that. Yeah, basically, I already said it, we inhale easier. Okay, inhale easier. Good. Third thing we have is this layer right here. Okay, but we're going to call this layer 3, and it's actually within here in this space right here, and this right here is called the parietal pleura. Actually, parietal pleura would be down there. This is the interstitial membrane, interstitial layer. Actually, no. This is actually called the alveolar basement membrane. Okay. Then we have another layer here, like an onion, and this one would be that space in between, and this is the interstitial space. So number 4, and that's right in there. Okay. Then this layer is actually going to be number 5, which is going to be the capillary basement membrane. And then we actually have one more layer that's going to exist here. Okay, one more layer, hang in there. And this one will be the capillary epithelial layer. Okay? These are the layers. This is going to be, like I said, alveolus. we want to label our PAo2 as 102 millimeters of mercury, and our PaCO2 as 45 millimeters of mercury, right? We want to draw a capillary bed in here. This time we're going to get a little fancy with it, okay? When we draw this one, we kind of want it to look like this. And then we're representing coming down throughout the body. Okay, just like that. Okay, pulmonary blood vessel capillary exchange. What happens with the capillary exchange is we actually have these CO2 molecules, right? Okay, these are CO2. Then we have over here in blue, we have our O2 molecules here, okay? What ends up happening is we have a structure in the blood called hemoglobin. Okay, we've heard of it a lot. We label it as HB. Hemoglobin has 4 binding sites. Okay? There's 2 stages of this. We have the T stage and the R stage, or we call it state. T state, and we have the R state. T state is going to be release. We call it the 10th state. Release of O2. And iron gets pulled down. So you have this iron molecule within the hemoglobin, which comes out and will attach to the oxygen, hold the oxygen on. If we go through this conformational change based on what the hemoglobin wants to do, it can pull in the iron, which is going to pop off the oxygen, which then puts it into this 10th state where we're deoxygenated. Hemoglobin will also bind oxygen until saturated. Okay? It's important. The R state is going to gain or grab O2, reach for it, and Fe gets pushed out, gets pushed up. Okay, so that puppy's gonna get pushed up. All right, so we know iron gets pushed up when we're in the R state. This is called the relaxed state. okay? So, for example, if we had hemoglobin full of O2, this O2 would want to come in here. When he does, let's say we had a red CO2 that was attached, it would then release and he would come up here into the alveolus. Okay, let me make sure I got everything on that. I got all those, got that, partial pressures, hemoglobin, continue adding oxygen until hemoglobin saturated, T state, pull iron down, O2 pops off. Well, I guess one thing I did forget is T state does a right shift. When you're losing oxygen, and when you're gaining, you do a left. I like to think of it like this. When you're doing good in life and you start losing things of the world, you do a right shift. You shift to the right hand of God. If you're starting to gain a lot of things of the world and you forget God, you do a left shift and you get away from God. All right? Hemoglobin will then travel this way. Right? Because this is venous return. Okay, and then this is arterial. Artery return is going that way with oxygenated blood. So now we come down to this area here and we find ourselves around this cell here. Well, what's going on in the cell? It's a great question. Citric acid cycle. That produces something called CO2, okay? We also have something called the electron transport chain. And what happens at the electron transport chain is there is this receiving of oxygen. So we have this like that, okay? We have something in here called hemoglobin. And what hemoglobin does is it's gonna take its O2, and the O2 will go to the electron transport chain. Now CO2, he's gonna do three things. One, he's gonna go to the plasma, which reminds me that O2 has 2% in plasma and 98% goes to hemoglobin. Okay? Really important to know. Right here with hemoglobin, one thing I wanted to point out was this. CO2 goes three places. 7% of CO2 goes in the plasma. 23% of CO2 goes directly to hemoglobin. Then, last but not least, we have, let's see, 70% goes and becomes HCO3 minus bicarbonate. This also has a friend called these protons that can come back and bind. So 70% of the time you're gonna need these protons that come and bind to hemoglobin. These things actually pop off oxygen and make it so oxygen can't bind. So when we talk about the T state, there's a couple things we want to know about it. There's actually 5 factors that we are interested in knowing. Number 1, if you increase in CO2 affects T state or leads to the T state, increase in protons. Number 3, increase in temperature. Number 4, increase in pH, or a decrease in pH, which also leads to the protons there. Number 5, 2,3-BPG also inhibits that, and this uses this enzyme called 2,3-BPG mutase. Okay? 2,3-BPG mutase. Now, 2,3-BPG mutase is going to do a couple cool things. What he does is we mainly see this with babies. And hypoxia. Oftentimes when the baby's squirming around, it's because they're becoming hypoxic. So they actually release cortisol, which actually stimulates the production of the type 2 cells, which increase surfactant, which actually decrease tension, surface tension, which allow for the expansion of the lungs. So when the baby's born, their lungs can expand, they can breathe. So if a baby's born premature, they have a really hard time breathing, and that's because they don't have that production of surfactant that allows for that decrease in tension, increase in compliance, and increase in volume, decrease in pressure, thus allowing for inhalation to occur easier. Now, hypoxia in babies. The reason I bring up babies over here with 2,3-BPG, or DPG, whatever you want to call it. I'm pretty sure it's called BPG. Yeah. Now, one thing that we want to know about this with babies is I'm pretty sure the babies, something with them allows the release of 2,3-BPG. So something with the baby is the placenta releases 2,3-BPG. And what happens as a result of that is the mom's O2 affinity mom's affinity to O2 decreases, but baby's affinity is high, so then baby takes oxygen. So baby does a left shift, and mom does a right shift. Because you increased in that BPG. Okay, and you caused for that to have that shift, and so the mom gets less O2, that pops off, you have less saturation on the saturation curve, and we'll talk about that. But the other thing I want to mention with this is carbon monoxide. Carbon monoxide poisoning. What this does is it actually binds to hemoglobin better than oxygen, and it takes place of oxygen spot, and so we're not getting O2, and it just totally shuts everything down. So that's what we need to know about carbon monoxide poisoning. Okay. I think I got everything here except for a graph, and basically the graph looked like this. It was similar to the one before with our shifts, right? If we had easier inhalation, we shifted to the left. If we had harder inhalation, it was harder to breathe, we went to the right. We called that a restrictive lung disease, and we called the one where you could breathe in easy but breathe out hard. Breathing out was hard. That's called an obstructive lung disease. Okay. Similarly, we look at this as percent of O2. Okay. And we look at this as saturation, O2 of hemoglobin, right? Let me see really quick here. Yeah, so it is saturation. So we have this right and left shift, okay? So let's say this dotted line, it's almost like a titration curve, like a T, like a, yeah, S curve or titration curve, right? So let's say for a second that this, let's just say that this, hopefully that's better. This dotted line is normal, okay? Normal. And let's say for a second as well that when we look at this, we want to think, okay, what is a right shift? What is a left shift? Okay? And a right shift would look like this. Okay? We decrease that slope a little bit. So we have a decreased slope. And we know that a right shift comes from a decrease in O2 to hemoglobin. And we know that that means that we have an increase in CO2. We have an increase in hydrogen. We have an increase in temp. We have a decrease in pH. Right? And we have an increase in B2, 3, B, P, G. Okay? Those are things that could cause it to shift to the right. Other things that could cause it to shift to the left could be something like this. Increased slope is what we get from the data. You would have a decrease in CO2, and a decrease in hydrogen protons, a decrease in temp. Okay, you'd have an increase in pH, which means you'd have an increase in bicarbonate. Then you would have, let's see, what else would you have? You'd have an increased slope, decreased CO2, decrease in hydrogen protons, decreased temperature, increase in pH, but you would also have a decrease in B2, 3, BPG. And that's really only active when you're in a hypoxic state. Okay? So this is what we mean by a left shift. Okay, and this is what we mean when we say that it's doing a right. Okay, a right shift. Okay? Okay, so T state, R state. So this would be in the T state. This would be in the R state. Right? T state, right shift. R state, left. T, you're getting closer to God, losing things. You're on the right hand of God, right shift, T state, left shift, R state. Okay, cool, coolio. So we got that down. Now let's move on to our last and final section. Okay, I'm gonna move these tables around so I can move this down. Hopefully we can get the rest of this in. I'll try to go really fast, okay? All right, so last thing we want to talk about is alveolar ventilation, okay? Okay? All right. Same thing that we did before. We're going to draw an alveolus. Okay, Sean. All right. Just going to label a couple things that we've kind of already labeled before. Okay, so I labeled this part here. PAo2 is going to be about 102 millimeters of mercury, and then PaCO2 is going to be about 45 millimeters of mercury. Okay. We know that the PAtmO2 is about 160, and we know that the PAtmCO2 is about 23. Okay, let me just double check that really quick. Okay, it is. We know that normal value would be 150 milliliters of gas within the dead space, right? So what ends up happening is you have this pressure that comes in. Well, we call this the TV. Stands for tubule tidal volume. And normal equals about 500 milliliters. Okay, and this is the amount of O2 within the breath that we take, right? Well, we also have another variable called TPV, and this is called total pulmonary volume. Okay, 1, 2, 3. Okay, this is called total pulmonary volume. What happens with total pulmonary volume is we take the number of breaths per minute and we multiply that by TB. So if I were to give you an example of this, it'd be like 12 breaths BPM, breaths per minute, times TB, and TB is normally 500 milliliters, and that would equal 6 liters, okay? But this doesn't take into account CO2 levels, or dead space. Okay, so if it's not taking into account dead space, it's not fully accurate. So one thing that we do to account for dead space is we do our AV value. Okay, alveolar ventilation. Let me make sure that's right. Yeah, I was right. So it's called alveolar ventilation, okay? And what this alveolar ventilation does is we take into account that we have 500 milliliters of fresh air. Call this fresh air, okay? Fresh air coming in. Okay, so if we have fresh air coming in, alveolar ventilation 500, then we subtract 150 milliliters from it. That gives us 350 milliliters, which then we times that by our beats per minute, which was 12 beats per minute, which then equaled our breaths per minute. So then 12 BMPs, breaths per minute, and that gave us like 4.2 liters, okay? And that's the actual amount that we're interested in the total amount of oxygen that's actually within this system. Now, if you were to use a snorkel, this would increase the length of the trachea, which would increase dead space. So it would change from 150 to a higher number, maybe 175, 200, okay? But we notice that it does have an effect and can be dangerous in terms of keeping your body in homeostasis with the oxygen CO2 exchange and getting fresh oxygen within you. Okay, I want to talk about one thing called VQ. This is the volume of blood flowing, and Q is the blood movement, and V is not that. V is actually the ventilation. So sometimes you can have a pulmonary embolism, which can actually decrease Q, but V stays the same. So pulmonary embolism, Q decreases, V stays the same. So then it becomes greater than 1. Yeah, that one affects Q, the movement of blood. Ventilation is actually affected by this thing called pink and blue. Let me think here really quick. Pink, that's like smoking, so decreasing C and Q cells. Let's see real quick here. Pink, buffer, emphysema, walls of alveolar damage, less capacity to inhale, hard to exhale. So pink, epithelial, walls are damaged, and that causes a easy or a decrease in elastin. So easy inhale, hard exhale. Blue is, I think they call it like second hand smoking. But it damages cells cover with mucus, which isn't good. And so it makes it hard in and out. Okay. Difficult breathing in and out. This actually leads sometimes to something called a, sometimes we can have low blood flow in pulmonary. Decrease, or that actually causes right heart failure, which causes blood pooling. Which then causes right heart failure, and that actually causes edema. Okay, I think that's everything. Let me double check. Okay, actually when V goes down, this is called a shunt, and then it leads to either hole or bronchitis. Then bronchitis leads to the blue, and it leads to the pink. Okay. Dyspnea is when it's hard to breathe for both. It's called dyspnea. Okay. Let me double check. Dyspnea. All right. Well, that's everything. So I think we're going to be good to go, but that should be everything here that we went over. All right. Thanks.